Keep moving. So, today, Thursday, 24th, you picked up your review. The reason why is the review tutorial is going to be Monday during tutorial. So you need to have it before we go through the review tutorial. I'm also going to make sure that the answers to this review are up online, I'm hoping by Saturday night. So you can look at it and go through it first by yourself, see if you can do it by yourself, and then check out the answers. And then if you have questions, we've got the tutorial on Monday and I've got after school on Monday I can help you with. Remember that the review is like the test. So if you cannot do the review, you cannot do the test. Okay? So make sure you can do that. You also have homeworks and Learn Smarts you need to get done before Wednesday next week. And I have not given you much time in class. I told you there wouldn't be much because of this lab. We are working on parts B and E today. We're going to finish the lecture for the rest of the chapter, and then we're going to go head back in lab. I'm going to explain how to do lab so that it will go fast and easy at the end of the lecture. So please pay attention. Make sure your lab's out and ready so you can look at it and make yourself little notes as you go through. I have put the solution to the problems that are in your notes up on every day from now till the test day. So it just says solutions to your problems in your notes, and there's the video for it. So try those. We're going to go back in lab in a minute. Yeah, if you want to run back real fast, you can. Okay, so let's go ahead and go to lecture. I'm going to start where I ended off last time, which was here. This is where you should have got to. We're going to finish it up. Remember also on the end of the lecture notes, there are also some multiple choice for you to try, and there's the right answers there, so you can look at those. All right. So we need to be able to look at something like this and be able to tell, is it exo or is it endothermic? So condensation, exo or endothermic? Hey guys, let's focus. Exo or endothermic? Condensation. Try it. Yep, exothermic. What about boiling? Endo, got to put heat in. What about sublimation? Going from a solid to a gas. That is also endo. What about liquefaction? Okay, right, it's coming down from a gas to a liquid. What about freezing? Exo, because you're going from a liquid to a solid. What about vaporization? Endothermic. Okay, so you should be able to look at these and be able to say really quickly which they are, which way the heats flow. Okay. Uh-huh.
From water going from like liquid water to ice, isn't that?
Exothermic, getting rid of heat that it has to become cooler. Okay, so now we're going to talk about evaporation and vapor pressure. So evaporation is where it's going from a liquid to a gas, right? Well, when we have vapor pressure, we're in a closed system. And we're going to worry more about vapor pressure on the last part of the lab that we're doing next time, which is part D, where we're doing it really quickly. Please make sure you look over that part D so when you come and I explain really fast again what we're doing, you know what we're doing and you can do it quickly, because then we can get back here and finish up the write-ups on the lab and any questions that you have that you'd like to go over, or work on Learn Smarts and homework. Okay, so just really quickly as we go through here, evaporation or vaporization is an endothermic process, going from a liquid to a gas. What do evaporating molecules carry away with them from the liquid? They carry kinetic energy away. And the kinetic energy equation is 1/2 mass times velocity squared, right? What happens to the remaining liquid? It becomes cooler because it's given up some of its energy. What is the process above called? Again, evaporation or vaporization. That's like a redundancy of number one. Condensation is an exothermic process where you go from a gas to a liquid or a gas to a solid. Usually when we go from a gas to a solid, though, it's called deposition, where we're depositing. Vapor pressure, again, is that pressure exerted by the vapor above a liquid. So if you have a pop bottle and you open it at room temperature, it fizzes pretty good, right? But if you took that same bottle and tried to open it on a really hot day and it was hot, it would really have a lot of pressure. It gets really tight. If you put it in ice, though, and cool it down, you could open up that same bottle and not have very much fizz because the gases stay in the liquid. Okay? And what type of molecules tend to have higher vapor pressures, polar or nonpolar? Let's think back to what we were learning about the intermolecular forces. There were 3 of them. Anybody remember what 3 they were? There are 3 intermolecular forces we talked about last time. Give you a hint. London dispersion forces and what? Dipole and hydrogen bonding. And hydrogen bonding was with nitrogen, oxygen, fluorine, right? So that, as we went from London to hydrogen bonding, it got stronger, right? That's like having a best friend and wanting to always hang with the best friend. You don't want them to move away. You want to hang with them. That's the same thing that happens with vapor pressure. So if I have hydrogen bonding going on, or if I have a dipole, which is a good friendship, maybe not my best friend, but a good friendship, I don't want them to go away, so I hang on to them tighter. London dispersion forces is, I'm in the same class with somebody, so what if they move away? I don't know them very well, not a big deal. So, what type of molecules have higher vapor pressures? What do you think? Which ones are going to go to gas easier? Think other. Polar, we're going to hold together. Non-polar, we're going to vaporize. Because non-polar, I don't have any investment in. So that's your London dispersion. So, non-polar, because they're not attracted to each other, they're not best friends, they're not friends even, they can go to gas very easily with a lot less energy. Instead of having that best friend saying, you can't move. You can't leave me here by myself, right? Okay, going forward. If I had 2 chemicals and I put them on the back of my hand, how would I know which one would vaporize first? What would I look at if all I had was that? I don't know how they really go together. You guys haven't learned what ethers are, so you don't know what they really are. If I put those on the back of my hand, which one would feel cooler? In other words, it would vaporize first. Okay, I have 1 vote for the left. How many say the blue on the right? How many say the green on the left?
You only have 2 votes,
I know, not everybody voted. The thing that you want to look at first is the molecular weight. So the molecular weight is going to be heavier here, right? So this side, the blue, is going to evaporate faster. Okay? The other thing that we need to look at besides the molecular weight, and you're going to have to do this on the test, is you need to look at is the molecule polar? Okay, is the whole thing put together polar? Well, you don't know what an ether is, but basically an ether is, for the first one, methyl ethyl ether, is a carbon, an oxygen, and 2 carbons. Methyl ethyl ether. Okay, so you have a methyl group, which is a 1 carbon, oxygen, and a 2 methyl group, which is an ether, or ethyl. And the oxygen in the center makes it an ether. The other one is a ethyl ether, so you have 2 carbons, 2 carbons. Okay? So I think the first one was supposed to be a methyl ether because it's only C2. I probably put the ethyl in there accidentally. So I look at that, but the oxygen's in the center of the 2 carbon molecules. Because it's in the center, I can't have a positive side and a negative side. So it's not a polar molecule. If the oxygen was on the end, then it would be a polar molecule. Okay? And then the last thing I need to look at is, does it have hydrogen bonding? Because if it has hydrogen bonding, the vapor pressure is going to go a lot lower. It's going to evaporate a lot less fast. So if it has nitrogen, oxygen, and fluorine directly connected to a hydrogen, as I'm looking at the molecule, then I know it's going to have hydrogen bonding. Okay? So those are the things you need to look at. If it has hydrogen bonding, the boiling point is going to be high, the melting point is going to be high. If it has dipole, it's going to be in the middle. And if it doesn't have anything, it's going to be down low. But you still have to take into account the mass. Okay? All right, going forward. So really quickly again, sublimation is going directly from a solid to a gas. It's endothermic. Melting point is the point at which it changes from a liquid to the gas. Changes to a solid to a gas. Basically, the liquid, it's equal to the vapor pressure. So decomposition. Now, this sort of just thrown in there. You need to understand that when we go through a phase diagram or a heating curve, we are not chemically changing the substance. We're just changing the phase. So when they talk about decomposition, don't get sucked in. Decomposition is a chemical change. It's not a physical change. Okay? Make sure you realize that. And then what substances are common? That's sublime, going directly from a solid to a gas. The one that you're most common with is dry ice, but water actually does that too. If you get to a low enough pressure, it will sublime. You've heard of freeze-dried foods, right? Ever had freeze-dried ice cream? Okay? Iodine also does that. If you take some iodine crystals in a container and just put it in your hands, it will warm it enough that it will go straight from a solid to a purplish vapor, which is pretty cool. All right, so going forward, we're going to do some math now. Hopefully you got a calculator. If not, grab one from mine. We're going to do some math. I'm going to show you the first setup, and then I'd like you to try B and C on your own. So we're going to be using the delta H, which is also called Q, is equal to mCp delta T equation. Now, this is known as the specific heat equation. This is really straightforward. She's not going to trick you in any way on this one, okay? So you just need to read it. Oh, here's mass. Here's where I'm going to get my delta T. And here's my CP. So I plug in. And I just use Q instead of delta H. You can use both. I'll put both. Yep. So I'm going to take my mass, 210 grams, times my specific heat, 0.39 joules per gram degrees Celsius, times my change in temperature, 95 to 40 degrees Celsius, and I just plug it through my calculator, making sure everything that I need to cancels out. Specific heat. I don't know why it's not SP, but it is CP. Okay, so we're plugging it through our calculator. We've got, we'll say 2 significant figures. The 40 really isn't, but we'll take it as 2. So 210 times 0.39 times, parentheses 95 minus, I should have done that in my head, 40 equals, I got calculator answer of this. Since we only have 2 significant figures, I should report 4.5 times 10 to the third joules. It needs to be in scientific notation because it's more than 1,000. Okay? Would you do the other 2 really quickly? I'll give you a head start. It's just a plug and chug, so it should be fairly easy. Yep, it's just a plug and chug. Is Aspen here? I need your medical form. So, okay, do you have a copy though? Okay, just get it to me next time, okay, please. Thank you. Yes, and I didn't have yours, Tian, either. Thank you. I didn't look down far enough. Nope, you're good. That's a J. Okay, how do we do? We do okay? Pretty easy, yes.
So if the temperature went down, the answer would be negative.
So that would be heat given off, yes. Yep. So most of these were heated. Yeah, all of these were heated. So if it was going down, I would just say it was a negative, that many given off, or the heat was given, that was given off was this many joules. Okay? All right, we okay? All right, going forward. This one right here, this is back to where we did the heat curve. Remember this curve like this? We can actually start with something that is frozen below its freezing point and end up with something that's above its, we've heated the gas. What you do is you do it step by step. So for most of them, like step 1, 3, and 5, you're going to use the Q equals mCp delta T. But for when we hit the flat spot, we don't change temperature, but we're putting energy in, right? So at our melting point and changing our to a gas, we are going to use Q here is equal to H of fusion times the mass. And here Q is equal to heat of vaporization times the mass. Okay, I want you to do the calculations. When you get all these calculations done, all you have to do is add them up to find out the total energy. One caution. Oftentimes heat of fusion and heat of, that's S, vaporization are given in kilocalories or kilojoules. If they are, you have to convert either steps 1, 3, and 5 to kilojoules or kilocalories, or steps 2 and 4 to joules or calories. I've been nice. I've given it to you all in calories. Would you take a time? See if you can figure out what it is. I'll start here in just a bit. I'll give you a 2-minute head start.
What equation are we using?
So for the steps 1, 3, and 5, you're using the Q equals mCp delta T. And for steps 2 and 4, I gave you the equation. And by the way, here's the mass right here, because they've had a hard time finding it last time. So we're going from ice at negative 30 to steam at 130. You have to break it down. It's 5 steps, not just one.
Wait, so for the change in temperature for step 1, we're only doing it for...
You're only doing it up to where it would melt, which is 0. So the first step is like, here's the first step from here to here. And then the second step is from here to here. That's 2. From here to here is 3. From here to here is 4. From here to here is 5. And then you have to add them together. Can't really see the 1. There's 1. So you have to chunk it to make it work. Do it that way.
What do we do with all the numbers?
You add them together.
You want to try to make them? That's 48.
Don't round until you've got all of them and you're adding them together. Having a hard time punching into my calculator here. No, that's what I got in my calculator. Is everybody getting what I'm getting so far? Let me see, this is what I got. That doesn't make, is that what you got? Okay, joules. Now, then I look back up here, I have 3 significant figures. I need to have 3 in my answer. That's going to round up. So I'm going to have to write it in scientific notation to show that I have 3, but it's also bigger than 1,000. So 10 to the 4th in joules, and that's my answer. Or I can put it into kilojoules and say it's 45 kilojoules, 45.0 kilojoules. Okay, so they could take it at any point. They could say, I have liquid at this temperature and I want it boiling at this temperature. So then you have 3 steps. Okay? Just know when it's flat line, it's just the fusion times the mass. Not a big deal. We okay? Everybody okay? All right, we're going to go lab. That's the last part of the lecture. For the notes, we're going to talk about lab. So grab lab out in front of the instructions and the other part so you can sort of follow along. We're mixing part E and part B. So you do need to have a partner as you're going back to lab because we're going to be doing 2 different things at the same time to get things rolling. So, first thing, one of you is going to go to the main lab. You're going to fill a large beaker, about 3/4 full with water, and you're going to place it on a hot plate and turn it to high. The other person's going to go to the back lab, do the exact same thing, place it on a hot plate, and turn it on high. Okay? You both have the same assignment. Then the person in the very back lab is also going to take a computer back there and leave it. Okay? The person in the main lab is going to grab a calculator that is charging on the north wall of that and come back to the area. Then both of you are in the main lab for this. Okay? You're going to pick 2 metals. I would like you to pick 2 of the specific heat metals, not the square ones that are out that are different, weird. Just pick 2 of the specific heat metals. Basically, tall one's aluminum. The one that looks like a gold, silver, it has sort of a gold tint, that's tin. If it has a blue tint, and you'll see it's really sort of a blue silver, that one's zinc. If it is, most of them have a little bit of rust on it, it's still. Okay? And then if it's copper, it'll be that copper color. So pick 2 of them. I don't care which one. If you choose aluminum, just make sure the water goes over it. Okay? When we do the next part. So you're going to weigh each, you're going to record the mass, you're going to record the color and size, and you're going to record the identity of the metal. If you don't know what it is, ask me, because you do need to know. Okay? All right, second part. You're going to carefully, and I do mean carefully, put these one at a time into the beaker so both of them are in there with the water. Okay? Please take the tongs from the top and come down and grab them. Use the beaker, or not the beaker, the crucible tongs, not the ones with the rubber on it, those are the beaker tongs, but come down and grab that little nubbin at the top there and pull it and put it straight in. So you're going to put it in like this, okay? So put it in, that one went below the beaker, it wasn't supposed to, and you're going to put that one in. So they're both in at the same time, okay? Then you have one more thing you need to do at this station before you go back to the back lab. We have to wait for this to boil, and so rather than waste time in lab, we're going to do things quickly. So you're going to wait for that. That's going to be boiling sometime. You're going to grab a styrofoam cup. You're going to weigh the styrofoam cup. You're going to get 100 milliliters of distilled water. You're going to pour it in the cup. You're going to weigh the cup again. Okay? Then you're going to take the temperature of the cup, water. Okay? Remember to plug the probe into the EasyLink and then the EasyLink into the calculator. Write down that temperature real quick. Then unplug the probe, turn off the calculator. You're done with this, go back to the back. Okay? Everybody okay so far? Okay, now in the back, you're going to each grab a beaker. One of you is just going to fill it with distilled water right from the jug. The other one's going to go back to the back into the ice machine, grab some ice, and then fill it with distilled water. Okay? You don't want too much ice in there, but you want about half of the ice, half of it water, because you've got to put an Erlenmeyer flask down into the ice water, and it's got to be all the way surrounded. So if you put too much ice, you can't get it all the way down in. Okay? All right. Then, the next part, come on, you're going to set it up like this. So you're going to have the syringe, and you're going to have the syringe all the way in. We found out last period you want it all the way to 0 to start with. Okay? And you're going to make sure this is open. Then you're going to connect this tube to the gas pressure sensor, and you're going to have a temperature probe in there also. Now we're going to be doing two things at once. So we're going to use the little veneer things that let us use more than one. That's why we need the computer. So you plug those in, you plug the mini USB into it, and then the USB into the computer. And then I'll walk you through how to set up the experiment in Logger Pro is what you need to bring up. Okay? If we have enough time, last period they didn't, we will finish the lab and do the pretty graphs. If not, then you'll probably either need to write those numbers down that we get from that back lab, or you're going to have to take a picture of it so you have those numbers when we come to class next time, or that you can do them at home on Excel if you want to. Okay, so the easy thing here is once you've got this set up, you're going to start in the ice water like this. You're going to do an events with entry. You're going to take a measurement. And then when you move to the next one, which is just your water, the thing that you want to do is you want to be able to keep the pressure constant. So whatever that pressure is in the ice water, that's what you want to keep. So you've got to remember what it is, and you move it to the other. And you're going to move this syringe up until the pressure is equalized at the hotter temperature. Because whose law are we trying to do? Who's under constant pressure? Charles. So we're working on Charles' law. We're not doing Gay-Lussac's. We're doing Charles' law. Okay? So Charles' law, we need to keep the pressure the same. Okay? On Gay-Lussac's, we'd keep the volume the same. The pressure would change. Right? So we're going to record that. Then we're going to move it to the hot water, and you record it there. Please be careful with the hot water because you're going to have a hot plate, and you're going to have tubes and wires that cannot touch them. Otherwise, they're ruined. So make sure you're careful. Once you got your third reading, you're done there. Close everything down and come back to the main lab. The main lab doesn't take very long either because by then, guess what? You're going to come back to water's boiling. And that's what we needed. So at water's boiling, you're going to take the temperature of the water boiling. Then you've got to cool down that probe before you can do anything else. Put it under some cold water, running water. Get it back to the original temperature of your styrofoam cup. Then put the temperature probe in your styrofoam cup. Okay? So I don't show the temperature probe here, but that's what you're going to put there. You're going to then, one at a time, move this into the styrofoam cup. Get the highest temperature. So your initial temperature is only going to be on sample 1. So whatever you chose for sample 1, that's the first one you're moving. Okay? So your initial temperature was sample 1's initial temperature. You'll move it. You'll get the high temperature. That's the final temperature water for sample 1. It's also the beginning or initial temperature for sample 2. So you're not going to take the metal out. You're going to leave the metal there. Then you're going to move the second metal into the styrofoam cup and get the highest temperature. When you're done there, dump out the styrofoam cup, dry the metal, put it away, put everything away, you're done. Okay? You decide how fast you're going in here. Goggles mandatory, aprons your choice. Let's go, break.
Question.
Yes?
Do you have another life jacket?
Maybe when we get back in here. Okay? Well, see, decide how fast and accurate you guys are. Let's move it. Got to be accurate, yeah.